So this picture, this one is what I illustrated before, the function which I call g of vx. This is a perfect Gaussian. So this is e to the minus vx squared over 2kt or something like that. Is a perfectly symmetric Gaussian around 0. Remember, that's why we got that the average velocity in the x direction is 0. What I want to discuss that, and keep this picture in your mind, I'll come back to it, but now I want to justify this, is the following. I want to close this. Okay. What I wanted to do is to calculate the distribution of the speeds. I have a distribution of the velocities. What I want to know is how many molecules, this is the problem that Boltzmann was after, how many molecules have speed between the number v and the number v plus dv, irregardless of in which direction they are moving. Because that's what experimentally is accessible to us. I will explain that later today. So that means the following, that what I need to do is now I know how many have one particular value of the velocity. It's this function that I wrote here. I want to count how many of those correspond to speeds between v and v plus dv. And you understand what that means. If we have, this is the plane of velocities, vx, vy, vz, and this tells me the distribution, how many states I have here, here, because this is the f of vx, vy, vz. That I know already. But now I want to know how many have total speed between a certain number and a little other. Well, you understand that the way a particle can have velocity, a speed v, is if vx squared plus vy squared plus vz squared square root happens to take the value v. And that is the equation of a sphere here in 3 dimensions, right? It's a sphere. This is a sphere of radius vx squared plus vy squared vz squared. If I say that vx squared plus vy squared plus vz squared is equal to v squared, which is the velocity squared, and this is the equation of a circle, of a sphere. In this case, just the shell of the sphere. If I want to know how many of them are between this number and this number plus dv, what I need is all the molecules that fall between the sphere of radius v and the sphere of radius v plus dv, which is a spherical shell. Okay? So I need to calculate what is the volume of that spherical shell and then multiply by the number of states that fall inside there, which I know how much it is because I already calculated in any region in space how much it is.
So the question is, how many states do we have between v and
between that have vx, vy, and vz such that the speed is given by this.
So it's about the states.
And you see,
not
yeah.
the particles.
Well, how many particles? I mean, these are the distribution of molecules. I'm counting molecules.
Yeah.
But I want to know how many molecules should I count? I need to count if the inner sphere has radius v and the outer sphere has radius v plus dv, all the molecules that fall here, whose velocities vx, vy, vz are such that they fall into this spherical shell, will have speeds between v and v plus dv. So I need to write the volume of this spherical shell, which we know what it is 4 pi v squared dv, because 4 pi v squared is the area of the sphere and the thickness is dv. And I have to multiply that by the number of states that fall there that are given by this expression. Okay? So, all in all, you see that what you will have, and that's what the picture here was showing. So now let me show the picture again. The picture is a better illustration than what I said with words. Here. So this is Vx, Vy, Vc. This is the sphere of radius V. This is the thickness dV. These are all the states that I was calculating before. I want to know how many fall here, 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 in all this sphere, in all directions. Because this molecule has speed V, so does this one, so does this one. Doesn't matter in which direction it's going. All those who are at a certain distance of the origin will have velocity V. So that's what I'm trying to calculate, and that's the calculation I will attempt now. So now, well, essentially you see what I am saying. Forget about this factor. What you see is that the distribution will contain the factor V squared multiplied by e to the minus m V squared over 2kt. And there are constants in front. I don't care, because the constant in front, I will get them by requiring, as usual, that the integral over all possible states gives me 1, because it has to be a distribution. But the important point is that the Maxwell-Boltzmann distribution, the number of molecules which will end up with velocities between v and v plus dv, is proportional to this, and obviously dv. Okay? So, contain a factor v squared. What does it mean? Simply that if I am counting states here, I count a certain amount, but when I'm counting states here at a bigger v, I have a bigger area that grows as v squared, and that's what gives me this factor v squared. So you see, the function I want is such, is with a constant in front, should be such that if I integrate over the whole space, and now I emphasize that I integrate from 0, because now I am doing a distribution of speeds, and the speed starts from 0, this integral should give me 1. So this integral with the constant in front should give me 1. So I'll calculate this integral to get the constant in front of the distribution. Okay, but from 0, pay attention to that. Okay, because we are talking about distribution of speed. You see, this is very similar to the I2 we calculated before, only that it's 1/2 of that. Because instead of starting from minus infinity, I start from 0, which means that I will get, instead of getting square root of pi over 1/2 of this over m over 2kt to the power 3, which was the I2, I will get the 1/4, simply because I am calculating half of that. That's the value of that integral. That means that the constant that I need to have in front will be the inverse of this number. Okay? Because since this gives me this, times the constant c should give me 1, c should be the inverse of this. So you see, putting all together, I get 4 over square root of pi. The square root of the 4 goes on top, the square root of pi comes on the bottom, and the m over 2kt goes on top to the 3/2. And this multiplied by v squared e to the minus m v squared over 2kt. So that is the Boltzmann distribution, the Maxwell-Boltzmann distribution. Okay? This is the number of molecules whose speeds fall between the value v and the value v plus dv. Okay, so that's the result that Maxwell and Boltzmann published. That Boltzmann republished based on the calculations of Maxwell, if you want, but we call it the Maxwell-Boltzmann distribution. So a couple of things. Sometimes in certain books, particularly in the Blundell, they will put the pi here, they put the letter pi here, and so they will put the pi inside here is the same. We can put this as 4 pi, and the factor is m over 2 pi kt. The book by Blundell uses that one, some other books use another one, I believe the one by Kittel use another one, but doesn't matter, it's the same. The constant is this one. I mean, you can always check. You have to integrate and get one if that's a distribution. So, first of all, let me show it to you. I had a picture here, and then I will obtain a few properties of them that now they are useful. This is the distribution. You see, it's clearly not a symmetric distribution. Well, first of all, it starts from 0, but it has, this is the v squared factor in front, and then you have an exponential decay, so this is not a symmetric curve. I will show you exactly what is shown here, that you have the maximum is in one place, but the average speed is another place, and the root mean square is in another place. We'll show that. But the point is that this is a distribution that it's not symmetric, and that's actually get it out of here, right? Get it out? No, get it out of here. But we want to explore a few characteristics. So the first one, we want to know what is the average speed of a molecule. That's a great interest. I mean, if nothing else, you are curious about what is the average speed of a molecule in this room. Do you have any idea, by the way?
Slow.
No, what do you mean? The speed is a positive number.
Oh, it's a scale.
Not the velocity, the average speed.
Millimeters.
You put a speedometer. How much, at what speed do molecules move in this room?
Millimeters.
What?
Millimeters per second.
No.
Well, we'll get the number and then we'll do it. Actually, it's not for today. In order to do that, we need to do a little more, but at least we can get a distribution. We want to obtain an expression related to temperature. Of course, that's what we want.
Can you get a spoiler?
Pardon?
Can you get an answer? How fast is it?
Yeah, we'll get it. I mean, if not today, next class, we will need to get that to see how much energy is there in the room. But for your information, I'm sure in physics, I discuss it with my students in physics, 2 normally. It's around 500 meters per second, the speed of sound, typically. 500 if you are talking about nitrogen. If you have a lighter gas like argon that there is a little bit in this room, it's probably 1,000 meters per second. But doesn't matter. That's not. We are not going to get numbers here. It depends on t, of course. So we need the integral. If the Maxwell-Boltzmann is f of v, we want to calculate v f of v dv between 0 and infinity. Okay? That's what we need to calculate. That's the average velocity. The average speed, not velocity. The velocity was 0, somebody pointed out. So you see that this is 4 over square root of pi, m over 2 kt to the 3/2. And I need the integral of v cubed e to the minus m v squared over 2 kt dv. From 0 to infinity, so as you see, this is the I3 that we are already using. And you know, the factor 2, we will put it here because remember, we defined I3 as 2 times the integral. So I3 was 1 over alpha squared. So we get 2 over square root of pi, m over 2 kt to the 3/2, and I get 1 over alpha squared. Alpha is m over 2 kt squared. Did I get it right? Yeah. So if I combine this correctly, I get 2 kt over m to the 2, and here I get it to the minus 3/2. So you get 2 kt over m to the 1/2. And I get the pi goes inside, and these 2 gets inside as a 4, I get an 8. That's the average speed. You will see that these things play a role, this constant. So it's, let me make sure I wrote it right, is square root of 8 kt over n pi. Good. That's the average speed. And the next thing we want to calculate is the average square speed, because we want to obtain the root mean square. And that is, of course, the integral, now the same constant in front, 4 over square root of pi m over 2 kt to the 3 halves. And now we have v to the 4 e to the minus m v squared over 2 kt. So you see all the Gaussian integrals that I told you had some purpose here. So this will give me the average, v squared. So I am taking the quantity v squared and I am averaging. I am not averaging v. Okay, and this is I4, so I have to again, remember my definition of I4 was from minus infinity to infinity, so this will give me 1/2 of that, because I am only integrating from 0. So I will write 2 over square root of pi m over 2 kt to the 3 halves. And the I4 was 3/4 square root of pi over alpha to the 5, m over 2 kt to the 5. And let's see what that gives me. So I have 2 kt to the 5 halves, but here I have it to the minus 3 halves, so I have it to the 1. So I have 2 kt over m to the power 1, combining this and this. The square root of pi go away, and I get 3/4, 3 halves. 3 halves times 2 is 3. So I get 3 kt over m. That's my result. Actually, I didn't need to do all this integral, because remember, we calculated already that the average of Vx squared was kt over m. And obviously the average of Vy squared is also kt over m, and the average of Vz squared is also kt over m. And the average of V squared, which is nothing else than Vx squared plus Vy squared plus Vz squared, can be nothing different from 3 kt over m. But I wanted to show you that the distribution is okay, that we could have obtained this result. And now I can obtain the famous thing I told you before, the average kinetic energy of a molecule in this room, which is 1/2 mv squared, is 3/2 kt. If I multiply by m and divide by 2, is this. And again, it's a specific case of the equipartition theorem, which tells me that per each degree of freedom, I get 1/2 kt. Have 3 degrees of freedom, I get 3/2 kt. I will show you later, today if I have the time, if not next class, the actual writing the equipartition theorem, and you will see that you didn't need to know all these details. That for any system which is quadratic in the energy, you will get this result. But here we'll get it. This goes directly to the equations of state and the things you learned in elementary chemistry, etc., that we will have to start discussing next time. But for the time being, one thing you can see here is that if you calculate, instead of v squared, which is what I calculated, you calculate this, which is what we call the root mean square. Instead of 3 kt over m, you get square root of 3 kt over m. What does it tell you? That the average root mean square velocity of a molecule is inversely proportional to the mass of the molecule. That's an interesting result because this tells you that when there are molecules moving around in this room, if you have a light molecule or a heavy molecule, on average the energy will be the same because the mass does not appear here. So when you have a mixture of different molecules, if one is 10 times lighter than the other, will still have on average the same energy, which means that it has to be moving much faster because, you know, a light particle to have the same energy as a heavy particle has to be moving faster. Indeed, we will later see that if we look at the molecules in this room, just for your information, and we will prove this thing, the molecules of nitrogen or oxygen move at around 500 meters per second, but when we calculate the same thing for a molecule of hydrogen, we will get 2100 meters per second, the molecule of hydrogen being 16 or 17 times lighter than a molecule of nitrogen. And that goes a long way to explain why we don't have hydrogen in the atmosphere and we have plenty of nitrogen and oxygen, right? Which is a thing that before the development of the ideas of mechanics was very difficult to explain because, you know, nowadays we know that wherever we point our telescopes in any direction in space, 99% of our universe is hydrogen. So it begs the question, how come that the gas world surrounding our planet doesn't contain hydrogen? And the explanation is that this number is much, much closer to the escape velocity than that number.
So it's actually escape the atmosphere?
Yeah.
Really?
I mean, if there was gas and if you leave enough, the molecules that move faster will not be found. I mean, escape velocity, you know, it's 11 kilometers, it's 5 times this, so you can say this cannot escape. But remember, there is a distribution. So if you have a distribution, the molecules here in the tail of the distribution will escape. And when that escapes, the distribution redistributes, and so if you give it enough time, all the light molecules will go away. And the atmosphere has been around for a long time. But well, that was one characteristic. So now that we know two important numbers, let me find the third one. The third one is what is the maximum of the velocity of this distribution. The f of v, I want to find this. Where does it have a maximum? Because remember, it's not symmetric. So I cannot say in the middle, there is no middle. So this is calculating a derivative. Remember, the function is, besides constants in front that I don't care, is v squared e to the minus m v squared over 2kt. Right? With constants in front that for the derivative do not matter. So I have the derivative will be 2v e to the minus m v squared over 2kt plus v squared times the derivative of this, which is the same thing, divided times the derivative of this, which is mv over kt, right? Times mv over kt, because I pull a 2 that cancels that 2. So if you look, we get 2v. I need to have the minus here, sorry. 2v, correct. 2v minus 2mv cubed over kt. No, minus v cubed over kt. Okay, minus v cubed over kt. V squared, v cubed, m cubed over kt is equal to 0. So that means that mv squared over kt is equal to 2. Okay, at the maximum, is that correct?
Yeah.
Yeah. So the maximum is when v is square root of 2 kt over m.
Which is 5.
That's the maximum. So let me write the three results now, one next to the other. V maximum is square root of 2 kT over m. V average was square root of 8 kT over m, and I have a pi somewhere. Yeah. And VRMS was square root of 3 kT over m. Okay, these three quantities, which are comparable, you see this is the smallest, this is square root of 2, this is square root of 8 over pi, which is 2.6 or something, this is square root of 3. So the maximum falls first, the average speed is to the right of the maximum, and the RMS is even more to the right, which is what that picture here was showing. Click it there, that was the picture I was showing. Yeah, that one. Here, so this is the maximum, this is the average speed, this is the VRMS. So that's the Maxwell-Boltzmann distribution. And we believe very firmly that this is the right distribution. And let me pass one slide and you will see why do we believe so firmly into this. We believe because somebody did this experiment that seems very simple, but it's anything but simple, and I want to discuss in detail. That's what they did. They took a gas in equilibrium inside that oven at a certain temperature, and they picked at the molecules that were coming out of here, and they measured the velocity. And you measure the velocity, and you build the distribution. If you ask me how do you measure the velocity, the idea is that you put some mechanism so that you count only the molecules with a certain velocity. So if you count for 2 hours the molecules of velocity 200, you know how many they are. Then you count for 2 hours the molecules of velocity 250, and you know how many those are. Then you count for 2 hours the velocities of the molecules of velocity 300, etc. And you build the distribution and you compare. Okay? So, and I will tell you exactly what you do because the story is quite interesting and has 2 interesting parts to it. So I am simplifying the story because when I tell you you measure the velocity, it's not that you put the air gun and you measure the velocity. What you have essentially is, I will show the picture that you saw there later, but you have 2 cylinders there. I mean, it's a big cylinder that's rotating, but the slit that lets the particle pass are not aligned. So, and this is rotating. So when this is rotating, this one passes here and they are rotating like this, so then this one comes to the front. If this one is moving at exactly the right velocity, it will pass through here. If it's moving faster, it will not, because it will hit after the slit passed. If it's moving slower, it will pass before this, it will reach before the slit arrives, and so you don't count it. So you make it spin at a certain velocity, and you count, and you know that you are counting molecules with speed, say 300 meters per second. Then you make it spin at a different velocity, and you count molecules coming at 320, and so on. So essentially, this is it. This is a very beautiful experiment. Kush and Miller did it in although there were preliminary results, but in 1955, they did a very beautiful verification of that experiment. And I want to tell you a little bit the details. So show for a second this picture, because that's the apparatus they use, which is a sort of modification of this idea. So this cylinder is rotating, the oven is here, you get the molecules streaming out, and they have to go through this slit. Okay, and since this spins at a certain velocity, you are only counting the molecules that are moving at exactly that velocity. I will do the math in a second, because if a molecule is moving faster, will hit the side and you will not count it. And if a molecule is moving slower, it won't hit. So you keep spinning and you count, and you will count how many are going at that velocity. Then you make this groove here spin at a different rate, and you count molecules with another velocity, and so on. And you build the graph. Let me see if I have here what they build. I will do the details later. This is the distribution they found, and this is, I'll make a comment later, this is not exactly the Maxwell-Boltzmann, but it's quite enough similar to the Maxwell-Boltzmann. I'll say where it interferes. This is the theoretical curve. These are experimental points of a few runs for different materials. So as you see, they actually verify that the molecules in a gas are distributed the way Maxwell and Boltzmann suggested. Let me see, yeah, that comes later. So let me go back to the notes and let me point two things. So they did the experiment, so to speak, in that tube, assume that the length of this groove that I mentioned is exactly L. So a molecule, in order to go all through the tube, will take how long? If it's moving with velocity v, L over v will be the time for the molecule to cross the tube. So you only will count molecules that happen since this is rotating and the angle phi of rotation is what? The angle phi of rotation is omega t. This is rotating at constant velocity. If the molecule, when you select a certain omega, you are selecting the time, because the angle phi is fixed, it's the angle between this and this, or the angle of the group, you are selecting exactly which molecules you will count. When you say you choose a certain omega, you say I will only count the molecules that manage to cross in this amount of time. And since the amount of time it takes is L over V, you are essentially selecting only the molecules that move with that particular velocity V. So you see, if you put these together, this is the time. What you are saying is that L over V has to be equal to phi over omega, or in other words, that the velocity of the molecule will be omega L over phi. Okay? Did I write it right? Okay, so you choose an omega and you count molecules of a certain velocity. You choose a different omega, you will count molecules of another velocity. By choosing the rate of rotation of that cylinder, because L and phi are parameters of the apparatus, you count the velocity you want. You have a question?
So is this going to measure the distribution of velocities with a single direction?
Yeah, you are counting. I am coming to that. That's a very good observation. You are not measuring exactly what's inside the gas. So if that were the word were as simple, you would measure the different velocities, you will plot how many molecules are from each velocity, and you would get the Maxwell-Boltzmann distribution that I just represented, something proportional to v squared e to the minus mv squared over 2kt. Okay? That would be my ideal world. If that happens, that I count and my molecules are distributed like this, I said, perfect, I nailed it. Actually, when you do the experiment, what you get is not this. What you get, unfortunately, is this. A different function, which is not quite the Maxwell-Boltzmann, with a factor v to the 4. That's what the experiment gives you. And this is related to two different aspects, one of which we will discuss next class, which is a statistical effect, so it's very relevant to our discussion of kinetic theory, but I will discuss it next. The other is an experimental fact that I will show you now. It's some problem with it, not problem, some characteristic of the experiment. The statistical fact is that, as you were suspecting, you are not measuring the distribution of the molecules that are inside your system, inside the oven. You are measuring the distributions of the molecules that jump out of the air. okay? So you are not measuring the distribution of velocities inside your system, you are measuring the velocities that come out of your system when you do a little hole in it. You can say, aren't they the same? Because the intuitive idea would be, well, they have to be related. The answer is yes, they are related. Obviously, if the distribution inside changes, what comes out when you do a little hole changes. But that is a different problem. It's called the effusion problem. You have a gas, you do a little hole, you want the distribution, to know the distribution of the molecules coming out. This is called the effusion problem, and it turns out that when you calculate the distribution of effusion, if the molecules are distributed like v squared e to the minus m v squared over kT, next time we'll see that the ones that come out have an extra factor of v here, coming from the fact. You can sort of have an idea how that is. You see, molecules that move faster are more likely to come to your hole and leave the system than molecules that are moving slower. So when you are counting the ones that leave the system, you are overcounting the molecules that are moving faster. And we'll do the mathematical detail next time. Intuitive, I believe, perhaps even Blondel says it as an example. He gives the example, say, imagine that you are trying to determine the income of the inhabitant of the United States, but instead of going house to house and just count how much money they have, you go to JFK and you stop there, and every person who leaves and crosses to go into the plane, you count the money. Well, you are not going to count, because obviously the people who are leaving are normally people who are a little bit well off than the typical person. So you will be overcounting the people with high V. And this effect, we will do the mathematics later. I mean, I am not pretending that it's the same thing, but this explains one extra power of V that you get. What is interesting for us is another factor which is related to the following, and that is an experimental detail that Miller and Bush very clearly analyzed. They said, imagine we have our little tube, and this little tube, say, has certain thickness. Okay? This is where the molecule has to go through. It's not infinitely narrow, it has a certain thickness, because if not, you are never going to get a molecule. So that means that you have more than just the molecules that can go straight. You can have the molecule that goes from here to here. So you are measuring a little range of molecules, because you are putting a little range of error. So you see, in some sense, you can say, if when this spins, if it spins enough for the molecule to hit here, you count it. If it spins a little slower and the molecule hits here, you also count it, because as long as it comes out, you count it. So in reality, although I say you count the molecules that have velocity this, you are counting a little more. You are counting the molecules, because you see they can be an angle phi plus, which is not just the angle phi plus this little extra that we will compute in a minute, or phi minus this little extra. So you are calculating the molecules between omega n over phi plus and omega L over phi minus, where phi plus is phi plus a little extra. Phi would be if they go straight. Phi plus is if they go straight but they end here. Phi minus is if they end here. So you are counting a range of molecules, because you know the V's you are counting are these, but if you are accepting all this range, you are counting a little range of velocities in your experiment. You're not counting just one velocity. And so you are calculating a sort of delta V, which is omega L over phi plus minus omega L over phi minus. Okay? And you are counting all the molecules in that range, and not just the ones you want. You are counting the ones you want and this little window. And if you calculate this little window, what is it? It's omega L phi plus phi minus times phi minus minus phi plus. Okay? So I'm just summing these two fractions. So it's omega L, roughly speaking, phi squared, because it's phi plus something, but I have here the delta phi. The fact that I am allowing molecules with a certain variability in the angle means that I am arranging molecules with a certain variability in the velocity when I count them. And if you want to count that precisely, what is the delta phi? If the tube has a width L, and you know, the tube has, well, let me show you the picture that I have here. Go back to the picture a second. So it's easier to show in that geometry than in my one by. No, the other way. Here. You see, if R is the radius of these two, L over R is the plus or minus in the angle. Okay? If L is the plus in this, L over R is the plus in the angle that you are allowing. So the variability in the angle, since it is the angle plus L over R or the angle minus L over R, so you are allowing an angle with a width of 2L over R. Now go back to the equation. And so you see you have omega L over phi squared 2L over R. R is the radius of my cylinder, and L is the width of this little channel, because I cannot make it 0. I would like to, but I cannot. And you see, this is your delta V. You can say, so what? Well, that, remember, omega L over phi was your V, so this is V to L over R phi. So you see your delta V ends up being proportional to V. So this error that you are making counts much more at higher velocities than at lower velocities, and it gives you an extra factor of V. That's why the V cubed, that would be what you should be obtaining, becomes a V4, V to the power 4. So that's a curious fact that I wanted to mention it because it explains the result of the experiment, and there is a nice discussion in the Blundell about that. So that's one of the experimental evidence. The other experimental evidence that we have about the distribution of molecules comes from something that has been known since the beginning of the century, which is that when we look at any spectral line of the light of any star, the lines are not infinitely narrow and they have a broadening. There are many reasons for the broadening, but there is one directly connected to the Maxwell-Boltzmann distribution. But it comes from the fact that the molecules that are emitting this light are not at rest with respect to us. They are moving. So in particularly the ones that come to us, and so we see the line, have a difference because some are moving in our direction, some are moving backwards, and that will give it a Doppler effect. You understand that if the line, for example, that line will be omega 0, say because it's hydrogen or whatever material that normally when the molecule is at rest emits at omega 0, we will see it as omega 0 times 1 plus V over C. Okay, this is the old Doppler effect. So if the molecules that are emitting have a certain variability in V, that will show up on a broadening of the line, because now the molecules will not all emit at omega 0, will emit at omega 0 plus or minus something. Okay, so let's say, to simplify ideas, that we are measuring the velocity in our direction. So let's consider the Doppler effect when the molecule comes to us. In reality, there is a correction for the angle there, but just to simplify, imagine that we are looking at the star in the x direction. The frequency that we will detect with our spectrometer will not be omega 0, will be omega 0 plus 1 Vx plus Vx over C. And this Vx
changes according to the Maxwell distribution, because are the molecules of the gas in the atmosphere or whatever the sun or the whatever star is emitting that. And we can calculate what this is. Okay, so let me just calculate how it shows up. So you will get, well, it's a plus minus, remember, because there will be molecules that are moving towards you. There are molecules that will be moving away from you. So omega minus omega 0, the discrepancy between the frequency you measure and the actual frequency the molecules were at rest, will be omega 0 Vx over c. Okay? So that much we understand. So that means that the Vx shows up as c omega minus omega 0 over omega 0. Because there is a variability on the Vx, there will be a variability in the relative spectral width of the line. Instead of being omega 0, will be in this window. Okay? So, what does it mean? That when you look at the distribution of the molecules, the f of v coming from the Maxwell-Boltzmann will translate itself in an f of w, in a distribution of the frequencies. And the f of w will be e to the minus m over 2 kt, and instead of v squared, we have that c squared omega minus omega 0 squared over omega 0 squared. So we will see a distribution in the spectral frequency that we measure. If we measure the line, instead of just seeing always photons arriving at you with frequency omega 0, will be in this range, and there will be the distribution, the Maxwell-Boltzmann distribution here translates itself in a distribution of the frequency. And that's essentially what you can measure. Just to put it in simple experimental terms, you say the maximum frequency would be, the maximum of the peak will be when omega is omega 0. And all this thing is 1. So, but the peak, let's see when the height is just 1/2, to have the half width of the peak. So we want to know for which value of omega this number, instead of being 1, for omega 0 this number is 1. For, let's say, for which omega this number is 1/2. So I want to see 1/2 equal to e to the minus mc squared over 2 kt omega 0 squared, and this is what I call omega half. But you understand what I mean by omega half. The omega, this is omega. The omega such that this omega, the peak falls to 1/2 from the maximum. That's what I want to determine. That will give me the width of the peak. And so now it's a matter of equating. Just take the logarithm. The logarithm of 1/2 is minus ln 2. The logarithm here is minus mc squared omega 1/2 minus omega 0 squared over 2 kt omega 0 squared. And from there we get, this is the delta omega squared. The delta omega squared, the delta omega, squared, because I have a square there, at half width, so the half width of the peak is the quantity I have here, 2 kt omega 0 squared over mc squared ln 2. All this number, 2 kt omega squared over mc squared. That's the delta omega. If you want, divide by omega 0 squared and take the square root, and you get the relative, the fractional half peak. Delta omega over omega. the relative width of the peak is this number, 2 kt ln 2 over mc squared square root. You see, by measuring the spectral width of the peak, or the relative spectral peak, I get information about the temperature of the planet. If I have independent information of the temperature of, say, the sun that I have, for example, well, you can check that the widths of the peak are what Boltzmann predicted, and indeed they are. Of course, this is not the only factor that broadens the lines of spectra. There are other things there that are more complicated. In a course in physics radiation, probably we will contemplate the origins of some other things that might be happening in the spectrum. But one of the typical is this, what is called the thermal broadening of a peak. The fact that any peak you look has a width, instead of being straight, is a little peak, coming from the fact that the molecules are oscillating, and so when they emit, they have the Doppler effect. So that's one of the other areas where these things are verified. So, and this is pretty much what I wanted to say about the Maxwell-Boltzmann distribution. Let me tell you in which direction I am moving. What we are going to do next time is actually what I would say is sort of, you know, when you go to a museum and you see the masterpiece, that would be the masterpiece of kinetic theory, which is what Boltzmann did, using the ideas of kinetic theory that I mentioned here and his distribution to calculate the equation of state of an ideal gas. In other words, you take a wall here, and we know that for a gas, the pressure times the volume is then kT, and this is a known fact that was known since 1800s. And remember, thermodynamics does not derive this relationship. This is called the equation of state of an ideal gas, but a little broader in terms of the ideal gas. And this was known, etc. You probably saw it in Chemistry 101 as Boyle's law, and whoever, many people were associated with that. From the point of view of thermodynamics, you don't derive this expression. Thermodynamics is a science that tells you the variables that describe a system are P, V, and T. And from some area outside this comes a relationship between them, so that out of the three, it's enough to determine two to know the state of the system. But this equation of state, thermodynamics treats it as a given fact. It says comes from some other area of physics. Indeed, there are other equations. The van der Waals equation is another relationship between P, V, and T. So you need to know which one you apply, and you don't derive it within the context of thermodynamics. Thermodynamics is about what conclusions can I draw from this, but I need to get it from somewhere. Kinetic theory derives this, actually calculates the molecules that are moving here, assuming they are moving with the Maxwell-Boltzmann distribution. So you calculate how many hit the surface at a certain angle. Of those, how much velocity do they have, then how much momentum do they transfer to the wall, then how much momentum per unit time, which is the force they transfer to the wall, and then how much per unit area, which is the pressure. So kinetic theory builds a theory of pressure that actually gives this result. And that was one of the great advances of kinetic theory. And for the first time, we could explain with a microscopic model some empirical relation that chemists and physicists as well have been using for 150 years. So that derivation is what we are going to do next time. We are going to obtain this, and once you know this, you can experimentally find at every temperature what is the pressure of a gas, how fast the molecules are moving, etc., etc. everything that today I said will come from this expression, but we'll actually derive it. So in a course in modern physics, or perhaps even in physics too, sometimes this is derived in a sort of approximation, without counting exactly everything. Kinetic theory counts it precisely, without saying, well, half of the molecules move this way, or hand waving. We are going to do it precisely, and that we'll do next time. And then we can deal with the problem of effusion, the problem I was mentioning, the velocities of molecules coming out of a system as opposed to in equilibrium inside the system. And we will move a little bit in kinetic theory. So I plan to spend, say, 2 more lectures in kinetic theory before going back to statistics. Okay, so we stop here, and as I told you, tomorrow I have to prepare an exam, but I will give you between tomorrow and Wednesday a few problems on everything that we have been discussing after probability.